so now let's think about this equation a little bit differently. I want to do a space-time discretization, and then think about how this solution might be computed numerically, and maybe garner some geometric intuition based on the discretization of the Laplacian in Cartesian coordinates. So let's just consider a system in R3. Okay, so let's suppose that we're working in R3, and let's consider a discretization of R3 into a lattice of some uniform spacing, epsilon. Okay, and now let's look at a single specified point of the discretization, and we're going to observe its neighbors, so the neighboring points. And what we're going to find is that each of these lines, which is oriented in the coordinate directions, which are the canonical Euclidean frame of R3, each of these lines, it can be discretized as kind of a second derivative within this direction. Okay, so we know that for example, the discretization of the second derivative in one dimension is given by u, and then we're going to isolate a coordinate. So let's say u of x plus epsilon y z, and we're going to fix a time value t, and then subtract twice u of x, y, z, t, and add u of x minus epsilon t, or epsilon, excuse me, x minus epsilon, y, z, t. And then I'm going to divide this expression by epsilon squared. This gives me the discretization of the second derivative in the x direction. Okay, so this is actually just a one-dimensional discretization rule. It's given by the formula of the Taylor series. Okay, so the reason why we choose this particular weighting of the points, where we assign this point relative weight 1, this point 2, and this point, or I guess negative 2, and this point 1, the reason why we assign these values is entirely due to the Taylor expansion. And I have a video talking about the Taylor series on my YouTube channel. When you take the Taylor expansion and you essentially, I mean, we can go ahead and do it. Why don't we just do it? So u of x plus epsilon is going to be equal to, let's just forget all the other variables because we're considering them to be constant, okay? So u of x plus epsilon is equal to, according to the Taylor expansion, u of x plus epsilon u prime of x, okay, plus epsilon squared over 2 u double prime of x, okay? Should be correct. And then similarly, u of x minus epsilon is equal to u of x minus epsilon u prime of x plus epsilon squared over 2 u double prime of x. And so if we go ahead and add these two equations together, we can solve for u double prime of x. And the u prime of x cancels. So the first order terms of the Taylor expansion cancel, and so we're going to get a second order approximation, okay? And so if we solve for u double prime of x in terms of u of x plus epsilon, u of x minus epsilon, and u of x, we get precisely this expression that I've already written here. And so this is going to be our discretization of the second derivative. Okay, so u double prime of x, which is going to be partial squared over partial x squared of u. And this is approximately given by this expression, okay? So we're going to do this in all possible coordinate directions. We just did this in the x direction. We're going to go ahead and do it in the y direction and the z direction, which will add, let's see, -4 and -6, like so. Okay, so these are the weights that we're using. We're taking a weighted sum of these points, the values of our function at these points, and we're taking a weighted sum in order to approximate the Laplacian. Notice the Laplacian is just the sum, and if you expand the Laplacian in the Cartesian coordinate frame, it's just the trace of the Hessian matrix, which is the matrix of second derivatives in the Cartesian plane, and so take the trace of the Hessian, you get the sum of all of the second order partial derivatives. So you get partial u over partial x squared plus partial u over partial y squared, right? This is equal to partial squared u partial x squared plus partial squared u over partial y squared plus partial squared u over partial z squared. And so we can form all of these discrete approximations of the second derivative in one dimension and then just sum them all together. And that will give us the discretization of the Laplacian. And we can interpret this quantity, right? We look at the weighting of it. We're taking the Laplacian to be the weighted sum up to some scaling factor, the weighted sum over this over these points in space, which is called a stencil. Okay, so we're taking the weighted sum over this stencil, and we can interpret this as saying the Laplacian is somehow a measurement of the deviation of the central value from its neighborhood points. So the value of the solution at the center of the stencil deviates from the value of the average value of the solution around that point, and this deviation is measured by the Laplacian. Okay, so essentially I'm taking an equal weight of these points. Let's suppose that the function takes values which are blue. So blue will be like a higher, we're using a coloring system which is going to be in line with the frequency spectrum of light. And so the blue, any part of my graph which I draw in blue, which is a way to kind of encode a four-dimensional piece of information into 3 dimensions here. If I write this as in the blue color, that means that the value of the function is relatively high compared to the average. And if I draw in pink, this is going to mean it is relatively lower, so a lower value of the function in accordance with the frequency spectrum of light. And so here, the Laplacian in this diagram that I've drawn, would the Laplacian be positive or negative? Okay, so the answer is that the Laplacian is actually positive, okay? So this is like, we denote this as like a positive curvature. And that means that the value of u at the center, the value of our solution at the center, is relatively less than its local average of its neighbors, okay? The local average of the neighbors is a higher value than the value at the center point. That gives a positive curvature and a positive Laplacian, okay? And then of course we could, if these points were, let's say, all red and the central point was blue, then we could say this is a negative curvature and the Laplacian is negative. And so if we fix the values of these surrounding points in blue, let's suppose that we now fix the values of the surrounding points in blue to be some large value that's fixed, and we just allow the time evolution of this central point of our stencil. What will happen to the value of u in time. So the idea is that, well, we can actually solve for this, okay? And how would this be done? Well, we know that the Laplacian of u is going to be equal to this sum of the outside values. Let's call this outside value maybe capital A or lowercase a. All right? And so this is the value taken at the neighbors, and we're assuming and here, here, and here. And then let's assume that the center point starts at an initial value, let's say u naught, okay, at time t equals 0. So now the Laplacian is going to be 6a approximated by 6a minus 6 u naught over epsilon squared. Okay? So it's just a constant. We're assuming epsilon to be fixed now. A constant times a minus u naught. And we're assuming that this is greater than 0. Okay. So then we're going to observe that if u solves the wave equation, then if we allow this u naught to vary now with time, and we change this to a u of t, we understand that time evolution of this system is governed by constant times a minus u. And we obtain this differential equation. And this differential equation is just, we can solve for it explicitly in time, okay, for a fixed spatial point. And what will that solution be? Yeah, what will the solution be? So we can put this in the form of the characteristic equation. Okay? So if we want to solve utt plus cu is equal to ca, we can write this in the form of this is a non-homogeneous ordinary, we can view this as a non-homogeneous ordinary differential equation in time that's linear. And so we should be able to just use the characteristic equation for the homogeneous part, solve the homogeneous equation, and then add a particular solution, get a complementary solution and add a particular solution. So let's quickly solve this differential equation here. Okay, so let's first consider the homogeneous piece. Tt plus cu is equal to 0. This has characteristic equation r squared plus c is equal to 0, which tells us that assuming c is positive, which it is, then this is going to give us solutions plus or minus I square root of c, if I'm not mistaken. And so this is going to yield solutions of the form a cosine of root c t, t, and this coefficient is now a function of x, plus b of x sine of root ct. So this is the particular, or sorry, this is the complementary solution. And then for the particular solution, we want to assume that our function has the form of a constant. And we see immediately that if our function has the form of a constant, then a constant in time, then this equation is immediately solved by setting u is equal to a. Okay, so u equals a is the particular solution. Notice that u equals a, we're assuming the outside values to be fixed. And we're only allowing the inside to vary. So that's a critical reason why a is just a constant and this particular solution works. And so we get that our general solution is the form of some wave given by the complementary solution added on to a particular solution, which in this case is some constant value. This is the equilibrium point of the wave. And then the amplitude of the wave is going to be the square root of a squared plus b squared. And that's the amplitude of the wave here, which about which this point will begin to oscillate. So to solve this more rigorously, I believe we would need, or like to specify these coefficients, we would need more data about the initial velocity, right? We've only given one piece of data, which is the initial value, but we might need to know the initial velocity in order to fully solve this equation. But just from the general solution alone, we are determining that this is going to exhibit wave-like behavior. This central point is going to be oscillating around some equilibrium value a, and it's going to be oscillating according to some amplitude, which is this square root of a squared plus b squared. It's going to depend on the initial velocity and the boundary data. And also, we can identify the frequency of the oscillation. The angular frequency of the oscillation is the square root of this constant c. And constant c, if you recall, was 6 over epsilon squared. And so the square root of c is going to intimately depend on the grid spacing. So in this case, if our grid spacing is epsilon, then the angular frequency is going to be of the order 1 over epsilon. Okay? And so these are all things that we can observe just immediately by just looking at the discretization to understand, okay, why is this a wave equation? And this is why. This is why. Because, you know, if we look at the discretization alone, we're getting wave-like behavior. And obviously we did fix the boundary points, but in a general wave problem, you're going to have to fix some boundary, okay? And you're usually going to assign a fixed value along the boundary. And in that setting, you know, this emergent, we should expect from the microscopic setting in the discretization of wave-like behavior, this emergent macroscopic wave-like behavior of our system, okay? So oftentimes doing the discretization can be a very useful tool in gaining geometric intuition and understanding what's happening locally. And of course, now, if you want to consider the true wave equation, you're going to have to consider the fact that these boundary points are no longer going to be fixed. And so all of a sudden, doing this, finding the solution here, given a is not a constant, is going to be quite difficult. You're going to have a much more non-trivial partial differential equation that's going to arise here. And so this method would not work, obviously. So it's more of just like an interesting kind of visualization, but the true mechanics is more complicated on a larger scale, okay? But, you know, it is kind of nice that when we do the discretization, out pops a wave equation, right? That's what we should expect. That's what we should want from a partial differential equation that's named the wave equation. What should I say about this? Yeah, so turns out the Laplacian is spherically symmetric, and so it obeys this very nice spherical symmetry. And so the way we're going to actually solve the wave equation and create a representation solution for the wave equation is actually by looking at the average value of u over spheres. So this is the average value of u kind of over a neighborhood, an epsilon sphere, you could say, a discrete sphere. It's the average of this, the difference between the value of u at the center and the value of u over this, its average over this discrete sphere. And we can generalize that to a continuum where we take the averages over spheres, over actual spheres. We fix a point x in our domain. We look at the average value of u on a sphere centered at that point x. And it turns out that by looking at fixing a point x and just looking at the average value over spheres of this true solution, one obtains a one-dimensional differential equation which can be transformed into a wave equation, into a one-dimensional wave equation, and then D'Alembert's formula can be used to kind of solve that one-dimensional equation explicitly. And this is kind of the key bridge that allows one to produce a representation solution, a true representation solution for the solution of this partial differential equation in a much more general setting. But even in this introductory discrete setting, we can already see this averaging over spheres kind of property of the Laplacian, or how the Laplacian works. It basically compares the average of a local sphere of the function, the average value of the function on that local sphere, to the value at its center. The Laplacian kind of compares those two values, as we're seeing in the discrete setting. And this spherical symmetry allows one to perform a change of coordinates and essentially transform this PDE into an ODE in the radial direction. And that allows one to solve and gain an explicit representation solution for the full wave equation. So it's a very, very powerful approach, and we can kind of gain a lot of motivation by first looking at the discrete setting. If you were to think of how someone would have invented this, the methods that we're about to see in the following lecture on the wave equation, if we want to think about how someone invented them, well, they definitely needed to observe spherical symmetry. They definitely needed to understand what the Laplacian meant geometrically, and the fact that, you know, it has this spherical symmetry, and also the fact that at its heart, the wave equation is essentially looking at a sphere and looking at the values of the function and the values of the function around that sphere, and then applying some elastic force based on whether or not, if the function's value is less than the surrounding points, then this force will be acting in the upward direction and pull the value up closer to its neighbors. But it's a force, not a velocity. So it's going to produce a wave-like motion, wave-like acceleration around an equilibrium. And similarly, if the values of the function, if the value of the function is less on this sphere than the value of the function at the center, then the second derivative will be negative and will push the value of the function. The force will be negative, I should say. The force will be negative and push the value of the function back towards equilibrium. So it's a restorative elastic force. And the restorative property of this force is essentially captured through the geometric interpretation of the Laplacian, and making sure that you orient the orientation of the Laplacian is correctly in sign. The sign of the Laplacian is in sign with the restorative force to give you wave-like motion around an equilibrium. Okay, so this hopefully that's helpful, and let's continue forward into the continuous setting of Rn.